In Chapter 8, we discuss solids, liquids, and gases and what the distinction is between these three phases of matter. To begin with, we're going to start talking about what's called intermolecular interactions. So matter commonly exists in one of three states: solid, liquid, or gas. And it's interesting to ask ourselves, how is temperature related to the state of a substance? Well, you're probably aware that when things are very cold, we get the solid state. So if we take a sample of water and we cool it down enough, it will turn into ice. So temperature is related to the movement of particles. And in particular, we know that when we heat a substance up, the particles that make up that substance move around more. So this tells us that in solids, the particles that make up that object can move around very little because solids form at low temperatures. Gases, like steam, form at high temperatures. And so that means that in gases, the particles that make up a sample of a gas are moving around a lot. Liquids form at temperatures intermediate between where we see gases and solids. And so that means that the movement of particles in liquids is, well, intermediate between what we see in solids and gases. So we might think of the particles in liquids as moving around a little bit, but nowhere near as much as in a gas and more than in a solid. It's also useful to think about how pressure is related to the state of a substance. We know that if we apply a pressure to something, we're going to push the particles that make that thing up closer together. So pressure is related to the space between particles. Now, if I take a gas and I apply a pressure to it, it will eventually become a liquid. And so that tells me that in a gas, the particles are further away from one another than they are in a liquid, and vice versa. In a liquid, the particles are closer to one another than what they are in a gas. If I continue to apply a pressure to a liquid, it will eventually become a solid. And so that tells me that in solids, the particles are even closer together than they are in liquids. So we can learn a lot about these three states of matter by thinking about how temperature and pressure affects them. An interesting question to ask is, why are some substances gases at room temperature and others are either liquids or solids? So for example, the element hydrogen is a gas at any temperature above minus 253 degrees Celsius. So at any ordinary temperature, hydrogen is always going to be observed as a gas. Now, water melts at 0 degrees Celsius, so below 0 degrees Celsius it's a solid, and above 0 degrees Celsius it's a liquid, and it boils at 100 degrees Celsius. And so what that means is that above 100 degrees Celsius, water will be a gas. So what is going to be a liquid at room temperature? Sodium chloride, which is a classic ionic compound, has a very high melting point, 801 degrees Celsius. So that means that below 801 degrees Celsius it's a solid, and above 801 degrees Celsius it's a liquid. Sodium chloride becomes a gas at 1413 degrees Celsius, which is definitely a very high temperature. An important trend to note is that ionic compounds are all solids at room temperature, whereas covalent compounds can be either solids, liquids, or gases at room temperature. And it's also worth noting that elements, rather than compounds, can also be either solids, liquids, or gases at room temperature. So the temperature at which a substance melts or boils is determined by the strength of what we call intermolecular forces, that is the attraction between the particles that make up that substance. In a gas, the intermolecular forces are relatively weak, and as a result there's a little attraction between the particles, and so they kind of move around independent of each other, and it's also why they spread out from one another, and a gas will disperse throughout its container. In a liquid, we have intermediate intermolecular forces. The particles are close to one another, touching, and moving around very little because they're quite strongly attracted to one another. In a solid, the particles are firmly attracted to each other. We have very strong intermolecular forces, and the particles try to get as close to each other as possible and organize themselves in a regular repeating pattern that we call a crystal. But the take-home message here is that strong intermolecular forces gives rise to high melting points and high boiling points. A classic example of a solid that's not an ionic compound are what we call covalent network solids. These substances have very high melting points, and they are composed of crystals, but they're not ionic compounds. They're made of nonmetals, and they're held together by an extended network of covalent bonds. It's almost like they're one giant molecule. Now, the classic covalent network solid is diamond, which is made of carbon atoms, but it's kind of interesting. In diamond, every carbon atom is bonded to 4 others in a tetrahedral arrangement. So every carbon is bonded to 4 others, and this creates a very strong network of covalent bonds, and as a result, diamond is very hard. Another example of a covalent network solid is silicon dioxide. In silicon dioxide, we have silicon atoms that are bonded in a tetrahedral fashion to 4 oxygen atoms. However, each oxygen atom is bonded to 2 silicon atoms in a bent fashion. So in carbon, every atom is bonded to 4 others, whereas in silicon dioxide, silicon is bonded to 4 other atoms, but oxygen is only bonded to 2. So the net result is that carbon is much harder than silicon dioxide, which is why you can use a diamond to scratch a window that's made of silicon dioxide. Ionic solids have really high melting points, as we noted before, and ionic compounds are made of crystals which are composed of oppositely charged ions. And what this is really telling us is the interaction between 2 ions is very, very strong. The interaction between oppositely charged ions is very, very strong, and that's why these ionic compounds have such high melting points. Classic example of an ionic compound is sodium chloride, which you probably know as salt. So, we've looked at covalent bonds, we've looked at the bonds between ions, but it's also important to recognize that molecules might be polar if the distribution of electrons around their central atom is not symmetrical. And we talked about this in section 4.5 if you'd like to have a review of that. So for example, the central atom in HCl is chlorine, and you can see we have just a single polar bond here. It's not symmetrical around the chlorine, so all of the electrons are being pulled towards the chlorine end of the molecule, so this is a polar molecule. In BCl3, we have a boron attached to 3 chlorines in a trigonal planar fashion. You can see that we have complete symmetry around the central boron, so boron trichloride, BCl3, is non-polar. This is the molecule formaldehyde, CH2O, and you can see around the central atom here, it's not symmetric, and the electrons are actually getting pulled up towards the oxygen end of the molecule, meaning that CH2O is polar. We see a similar scenario in ammonia. So we have the central nitrogen. On one side it has the lone pair. On the other side it has the 3 hydrogens, so it's not symmetric around the middle. That makes it polar. And if we consider the individual bond dipoles, we can see that the electrons are being pulled up towards the nitrogen end of the molecule. CHCl3, if we look at the central carbon, you can see on one side we have hydrogen, but on the other side of that central carbon we have 3 chlorines, making it asymmetric around the central carbon. And if we can consider the bond dipoles, we can see that all of the electrons are being pulled down to the chlorine side of the molecule, and that this molecule is very obviously polar. However, if we look at something like CCl4, when we look at the central carbon here, we can see that it's completely symmetric around the middle there. We just have 4 chlorine atoms attached to the central carbon. They're all exactly the same. And so this renders CCl4 non-polar. So why is this important when we are considering intermolecular interactions? Well, if a molecule is polar, it will have a positive end and a negative end, or we will say that it has a dipole. And what this means is that the positive end of one molecule will be attracted to the negative end of another molecule. And we call this kind of attractive force a dipole-dipole interaction. So dipole-dipole interactions will occur between any polar molecules, and they'll serve to raise the boiling and melting point of that substance. So what we're really saying is that we expect that the boiling and melting points of polar compounds to be greater than the boiling and melting points of non-polar compounds. There is an especially strong type of dipole-dipole interaction that is called a hydrogen bond, and you should learn to recognize the potential for hydrogen bonding. Hydrogen bonds form between a hydrogen atom that is attached to oxygen, nitrogen, or fluorine, and another oxygen, nitrogen, or fluorine on a different molecule. So a good example of this is the hydrogen bonding that exists between water molecules. So here we have our hydrogen atom that is attached to oxygen, interacting with oxygen on another molecule. The hydrogen has a little bit of a positive charge, the oxygen has a little bit of a negative charge, and it's actually a dipole-dipole interaction, but it's an especially strong type of dipole-dipole interaction because when hydrogen is attached to oxygen, nitrogen, or fluorine, we get a very polar bond. And it should be pointed out that the hydrogen end of the bond is always the positive end. So hydrogen bonding gives rise to high boiling points, and the boiling point of water is much higher than we would expect if it wasn't for the hydrogen bonding. Hydrogen bonding is very important in biochemistry because it determines how ligands interact with proteins. It also determines the shape of proteins, what we call the secondary and tertiary structure of proteins. And it is also why we see base pairing in DNA and DNA coiling. So looking at some structures that we see commonly in proteins, one structure we see is called an alpha helix. It gives rise to rod-like structures in the protein. And you can see we've got a hydrogen on a nitrogen that is interacting with an oxygen atom in a different part of the strand. And we see that all the way through, and it results in these alpha helices. Another type of structure common in proteins is what we call a beta pleated sheet. This is how the protein kind of makes a U-turn, the protein chain. And again, you can see we've got a hydrogen on a nitrogen interacting with an oxygen atom in each case, and that holds the protein in this U shape. When we think about DNA base pairing, we know that one base pair is the AT pair, the other is the GC pair, and you can see in each case we have a hydrogen atom that is on nitrogen interacting with either an oxygen atom or a nitrogen atom. Same for the AT pair, hydrogen that's on nitrogen interacting with an oxygen. And this one, we're missing a hydrogen atom there, but we see the same type of interaction. So we've learned about interaction between ions. We've learned about interactions between polar molecules, including the important hydrogen bonding. What about non-polar molecules? Do these guys interact with each other? Well, it's important to realize that London or dispersive forces exist between all substances. And this is a result of the fact that electrons are able to move around to different places in a molecule. So we're going to consider two hydrogen molecules, molecule A and molecule B. And on average, the electrons are shared exactly halfway between each of the two hydrogen atoms that make up each molecule. Now the electrons are able to move. So let's just say that in molecule A, they move a little bit to the left just for a moment. And this creates what we call an instantaneous dipole. The left of molecule A becomes a little bit negative, and the right of molecule A becomes a little bit positive. But now we have to think about what this does to the electrons in a neighboring molecule. Well, the electrons are going to be attracted towards the positive end of molecule A. So the electrons are all going to move to the left of molecule B. And so molecule B, its left end will become a little bit negative, and its right end will become a little bit more positive, and that's going to cause these guys to get attracted. Now let's think about what happens in a neighboring molecule. We have a positive here. It's going to suck electrons that way, and that's going to make that negative and that a little positive. And before you know it, this thing is just going to, through a chain reaction, this interaction is going to spread throughout our whole sample of hydrogen. So because the electrons moved just the once, suddenly we set up a scenario where we form a whole bunch of forces between the hydrogen molecules. So what we know is that London or dispersion forces tend to increase with the mass and size of an element or compound. So in this first column here, we have the noble gases, the group 8A elements, and as we head down the group, these guys get heavier. We can see their molar masses go up. But what we can also see is that their boiling points go up, and that's a reflection of the fact that the London forces between the atoms of these gases is increasing with the molar mass. Here we have a series of diatomic molecules, and we see the same pattern. As the molar mass goes up, the boiling point goes up, reflecting the increased dispersion forces between those molecules. Okay, so here's an example from the book. It says, order the following compounds of group 14 elements and hydrogen from lowest to high of the following compounds of a group 14 element and hydrogen from lowest to highest boiling point. Explain your reasoning. Well, so group 14 is also known as group 4A, and group 4A goes like this. It says carbon, silicon, germanium, and tin. So we're getting heavier as we go down. So if I was to draw out the Lewis structure for these guys, I would see that none of them are polar, because they're all surrounded symmetrically by 4 hydrogen atoms. They're all nonpolar. So that means that the only forces between these guys are London forces. So what that means for us is that there's no possibility of dipole-dipole interaction. So as the mass goes up, we would expect that the strength of the London forces go up and the boiling point will go up. So it's kind of an interesting situation. I think that they are already organized in order of increasing boiling point, because this guy has a mass of about 16. This one has a mass of about 32. This one has a mass of about 77. And tin H4, SNH4 has a mass of around about 121. So yeah, you can see as the mass of these guys goes up, I would expect their boiling points to go up. So methane is less than silicon tetrahydride, which is less than germanium tetrahydride, which is less than tin 4 hydride. Okay, what intermolecular forces besides dispersion forces exist in each substance? Are any of these substances solids at room temperature? Well, potassium chloride is an ionic substance. So we know that there are ion-ion interactions, and we also know that all ionic substances are solids at room temperature. Ethanol is a covalent compound. And if I look the structure of ethanol up, which is pretty easy to do, I see it looks like this. And so what I can see here is we have hydrogen attached to oxygen. So that means we have the possibility of hydrogen bonding. Okay. Now, is ethanol a solid, liquid, or gas at room temperature? Well, ethanol is the kind of alcohol you drink to get drunk, and it is very much a liquid. Bromine is a diatomic element. It's made of non-polar molecules, so there are no forces beyond dispersion forces, so nothing to say about that one. And then it says, are any of these substances solids at room temperature? And you may or may not have remembered is that bromine is one of the elements, one of 2 elements that's a liquid at room temperature. So there are only 2 elements that are liquids at room temperature. They are bromine and mercury, and you should remember that fact. Okay, and that concludes the section on intermolecular interactions.